Title of my talk is the Nonlinear Stress Intensity Factor in Fracture Mechanics and the Application. Outline of my talk is the following. First of all, as the introduction is some words about constraint effects. Then is the plastic stress intensity factor formulation. Next is the creep stress intensity factor. Then is some application of nonlinear stress intensity factor in the form of critical distance determination, surface crack behavior, mixed mode crack growth rate, creep and fatigue interaction, and finally will be some examples of real structural integrity assessments. Motivation of our study. As you know, in literature there are several constraint parameters. One of them is the in-plane constraint factor, that is T-stress, that is elastic constraint factor, Q factor, second order amplitude factor. This first three parameters is in-plane constraint factor. Next is stress triaxiality, TZ and TZZ parameters. Next is the AP area factor, and these three parameters are out of plane constraint factors. All of them, these constraint parameters, is additional parameters to main fracture resistance parameters like G integral and inertia. With my point of view, it's not convenient for practical point of view to use two parameter fracture theories to describe fracture resistance characteristics of real structures. To overcome these difficulties, we introduce nonlinear new fracture resistance parameters in the form of nonlinear stress intensity factors, which takes into account in-plane and out-of-plane constraint and interaction between in-plane and constraint effects. First, nonlinear stress intensity factor is the plastic stress intensity factor. Theoretical background of plastic stress intensity factor is a well-known Hutchinson-Rosengren-Rice solution. In this figure you can see the well-known solution of Hutchinson-Rosengren-Rice, and next equation is the described plastic stress intensity factor. Plastic stress intensity factor is a function of nominal stress, yield stress, Ramberg-Osgood parameters, elastic stress intensity factor, and governing parameters of crack tip fields in the form of IN integral. I would like to remember you that Professor Hutchinson introduced this governing parameter only for infinity-size cracked body. We elaborated and extended HRR solution and proposed numerical method on the basis of finite element method to determine this governing parameter for specimens and real structures. First of all, calibration of plastic stress intensity factor was given by describing fracture toughness behavior of structures steel. We tested the classical experimental fracture mechanics specimen, bending specimen, compact specimens. In these specimens was varied the range of dimensionless crack length, and specimen's thickness was changed. This combination of dimensionless crack length and specimen thickness give us different combination in plane and out of plane constraint interaction. Some experimental results. First of all, I would like to show you the behavior of governing parameter EIN integral along a crack front, for instance, for compact specimens, from free surface to middle sections of specimens, you see that this governing parameter is a function of specimen, taking into account specimen geometry and dimension is crack length. Next figure shows the variation of elastic stress intensity factor from free surface to middle sections of tested specimens. Now I will show you experimental results for fracture toughness determination. This figure shows K1C fracture toughness as a function of the specimen thickness and dimension is crack length for bending specimens and compact specimens. You see that there is a very large scatter band. And the question is that what is the fracture toughness of materials? Is the properties of materials or not? But if you use elastic stress intensity factor, you see the lower, you see that the elastic stress intensity factor is approximately constant for the same, for different specimen configuration, and is independent on specimen thickness and dimensionless crack length. With my point of view, that is the real properties of material, that is the real fracture resistant characteristics. So, another kind of nonlinear stress intensity factor is the creep stress intensity factor. As you know, another type of constitutive equation used to formulation of creep stress intensity factor, and next figure shows the creep stress intensity factor equation, which that is the creep stress intensity factor is the function of creep time and rate of displacement on the loading direction, and again is the function of governing parameters in the crack tip, in the creep condition. Contrary to elastic plastic solutions, this parameter is a function, not only dimensionless stress function, it is the functions of rate of displacement. And again, we elaborated numerical method to determine these parameters for creep conditions. So, and now I come to application of nonlinear stress intensity factor. For first example of application of nonlinear stress intensity factor is the critical distance determination for elastic plastic formulation and creep behavior. You see, to determine of critical distance, we have used strain energy density approach, well-known approach, and now I will see you the equation to determine critical distance. This critical distance is a function of main mechanical properties, main elastic plastic mechanical properties of materials and plastic stress intensity factor. Next figure show our experimental results. We tested again compact specimens and bending specimens with variation of dimensionless crack length and thickness. You see that is experimental crack front position for compact specimens. And that is the numerical data simulation of critical distance distribution along crack front in the thickness directions of specimen. So, and I would like to pay your attention on this figure. In this figure, represented experimental data for two kinds of steels with the same elastic properties, including fracture toughness. These two kinds of steels have the same Young models and fracture toughness, but you see that plastic stress intensity factor is different. Critical distance determination for creep conditions. Again, equation for critical distance determination for creep conditions, but in this case we used strain energy rate density. Again, equation for creep stress intensity factor, and you will see the distribution of along strike height and curvilinear crack front governing parameters as a function of creep conditions, as a function of creep material properties, and as a function of dimensionless crack length. And finally, I will show you the distribution critical distance for experimental tested specimens along the thickness directions, initial crack front position, final crack front position as a function of creep time, one type of stills and other types of stills, and finally we have found good relation between creep critical distance and creep stress intensity factor. So next application of nonlinear stress intensity factors, that is the problems of mixed mode crack behavior. You see, we tested and subject for our test and calculations two types of cruciform specimens, flat specimens, and cruciform specimens with thinning area. And I would like to show you the constraint effect. For instance, for flat specimens, you see the governing parameter is a strong function of dimensionless crack length in full range of mode mixity from pure mode 2 to pure mode 1. And other types of biaxial loading specimen is not sensitive to its loss dependence for constraint in full range of mode mixity. By using these results, we have got fatigue fracture diagrams. You see, fatigue fracture diagram, crack growth rate as a function of nonlinear stress intensity factor in full range from pure mode 1 to pure mode 2. So another example of application nonlinear stress intensity factor. That is the surface crack behavior. You see, the subject for our study is hollow cylindrical specimens and cruciform specimens with the initial surface flow with different aspect ratio. That is our test facilities, and I would like again your attention on the useful to use plastic stress intensity factor. We tested two aluminum alloys with the same elastic properties. You see the distribution of elastic stress intensity factor from free surface up to mid sections of hollow specimens. But next figure, you see the plastic stress intensity factor. Elastic properties are the same, but plastic stress intensity factor for the same loading conditions, you see different. Again, as a result, we have got different crack growth rate data. So, and last point for application of nonlinear stress intensity factor is the grip and fatigue interaction. That is our test facilities and test builder for crack and for grip and fatigue interaction, and that is material properties, static properties, and grip properties, and that is the fatigue fracture diagrams. In the classical form interpretation, crack growth rate in creep condition as a function elastic stress intensity factor, as a function of CT integral, and as a function of creep stress intensity factor. So, and last point of my presentation, application plastic stress intensity factor to structural integrity turbine disk. Subject for our consideration is disk, some loading history. At operation we have found quarter elliptical surface crack in slot fillets in a half of wheels. So, first of all, we carried out finite element method to determine elastic plastic stress and strain distribution at operation loading conditions. Operation loading condition is a startup shutdown cycle. And we have found that maximum equivalent stress realized in the deepest point of slot phase, and maximum value of equivalent stress is exceed the yield stress of material. So we have got elastic plastic behavior of materials. So traditional finite element meshes, plastic strain distribution on the free surface of disk and along cake front in the slot fillets. So, and then this is a distribution of elastic and plastic stress intensity factor for initial cake front position, from one free surface of disk up to inner surface of slot. That is the red points is the final cake front position. And finally, you will see the fatigue length curve. That is the crack length as a function of number of cycle of loading. You see that differences between elastic and elastic plastic solutions on the base of plastic stress intensity factor is increased with increasing of number of cycle of loading, or with the increasing of plastic zone size at the crack tip. And finally, some comments about my presentation. Elastic plastic and peak stress intensity factor reflects well the changes of stress-strain state as a crack tip from plane stress to plane strain, and is the most sensitive parameter because it's a function of elastic and peaked material properties. Second one, that the nonlinear stress intensity factor is useful for interpretation of fracture characteristics under static and cyclic loading and grip and fatigue interaction, and contrary to two parameters, fracture severity can be considered as the total constraint and fracture resistant parameters, which takes into account in plane and out of plane constraint parameters in the interaction. And finally, last point, the concept of critical value of nonlinear stress intensity factor was introduced and employed in much the same way as elastic stress intensity factor in classical fracture mechanics. Thank you very much for your attention.